Okay, so let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's jump into it. Okay. So before we begin, we do not have class tomorrow. Fordham is on break. So you don't have any classes tomorrow. And also, let me double check this here. Let me double check. Because it's around. So I have different classes at different times. Okay, yeah. So also, your test 1, is going to be a week from Friday. And yeah, I think it would cover looking at the syllabus. Probably everything we do up to Tuesday. Although, like on Tuesday, like we're going to be spending a lot of time on examples. So even though it covers everything up to like the same week, it's not really going to be anything new. It's just going to be extra practice. So yeah, so it's going to cover at least up to the chain rule. I don't know, I might not put implicit differentiation on it, or maybe put that as a bonus. But yeah, so your first test is on March 19th, which is a week from Friday. Okay, I have some other classes where their test is actually earlier. So no class tomorrow, first test on Friday from this week, which I should have done that. I was just in it. Okay, which means we do have a quiz also on the 14th, right? So that should give you some extra practice for the test. But yeah, and so we'll talk about the test a little bit more when it comes down to it. Essentially, the test is going to be more long form. So it's not going to be like, you know, multiple choice where you don't get partial credit. It's going to be like, you're going to show your work, you're going to write things out, you're going to scan it, you're going to upload it. I'm going to, you know, grade and make sure you kind of know what's going on. So even if you make a mistake, you get a wrong answer here or there, you know, you lose a couple points, but overall, I'll know you understand. And that being said, I think I mentioned that, I don't remember which class I mentioned this to, but I know that some of you aren't doing so hot grade-wise, but I just want you guys to know there's no reason to panic. That's actually pretty normal for things to start out a bit rough, especially when, you know, you're doing calculus with a new instructor and you don't really know what's going on. But yeah, you should remember that your quizzes, one is going to get dropped. It hasn't been dropped yet, so your grade is suffering from that. It's also suffering from the fact that the quizzes don't give partial credit. It's also suffering from the fact that when you do get your first test, the test would actually count for a larger percentage than the quiz would. And so when you're getting partial credit for that and you get a higher grade for that, it's going to bump you up. So it usually goes up after the first test. If after the first test, you're still in a bad position, then we can talk. At this point, though, I think it's very premature to be worried about your grade or anything like that, just in case anyone has been doing that. Did someone have a question? James?
Yeah, I just had a question about just the assignments on Cengage. If we don't get to chain rule and implicit differentiation, would those due dates change from March 17th?
Yeah.
Okay.
Yeah.
Gotcha.
We're definitely going to get to the chain rule, though. Implicit differentiation is the one I'm not sure about. But yeah. In fact, we're actually we're going to talk about the chain rule today. In fact, so let's actually just finally get into it. So those are just some announcements that I wanted everyone to be aware of. Okay, so last time we were talking about more on derivatives, and for the last couple of classes, it was just kind of like an information dump, or like a concept dump. I'm kind of just telling you, here's the derivative, here's what it's useful for, here's what it can tell us, here's why we care. Here are some strategies for figuring stuff out. So it was very kind of just information intensive. Now we're going to actually get back to actually computing stuff, working stuff out, doing what people usually think of when they say doing math, right? But just a quick recap of last class, we covered the first derivative test, which is a test that helps us figure out when a function is increasing, decreasing, has maximums or minimums. We knew that first we need to find the critical points where the first derivative is 0 or undefined, plot these on a number line and test points, random points on either side of them. And then we can conclude based on how those guys behave, whether something's a max or min or neither. But we can also always tell when something is increasing or decreasing. We also looked at the concavity test. This is what tells us about whether something is concave up, concave down, or there's an inflection point there. This one uses the second derivative. First, you find the critical points for this one, which is where the second derivative is 0 or undefined. Plot those on a number line. Same thing, except this time the number line is you're going to be plugging in those numbers into the second derivative instead of the first. And you conclude based on the signs of the second derivative. When it's positive, it's concave up. When it's negative, it's concave down. And if it switches from concave up to concave down or vice versa, and the point in between is the function is continuous at the point in between, means the graph actually passes through that, then you have an inflection. We put that in a summary because we always need to know, just as a quick reference, okay, if I'm looking for this, what function should I be looking at? That's going to be very important. So I told you what you can figure out based on which function and how you can figure it out based on each function. So the original function tells you about location, current status, position, things of that sort. The first derivative would tell you about speed, if it's an application, velocity, increasing, decreasing, maximums, minimums. You'd use the first derivative test to figure all those out. The second derivative will tell you about whether something's concave up, concave down, or if there's an inflection point, and the concavity test will tell you about that. There's also a second derivative test, which tells you about maximums and minimums using the second derivative, but it's kind of superfluous because you're already going to be doing the first derivative test, so you're already going to know where the max and mins are. And I just, for one, we don't need to know it. It's kind of useless. And for second, I just don't want to get into the confusion of people thinking that the second derivative, they think maximums and minimums and they think second derivative. It's not really a habit I want to encourage. Let's actually go on. We also spoke about the existence of a derivative, which was actually easier to talk about in terms of the negative when it does not exist. It does not exist if it's not continuous, or if there are sharp corners, or your function does some sort of weird behavior where you get a vertical tangent line. And that's kind of where we headed. So those were just some facts about the derivative. We're still going to start out with some facts about the derivative, but now we're going to talk more about some computational facts and properties. So let's actually get comfortable and get to that. So let's start with some properties. So we are now going into chapter 3, derivative rules and formulas. I actually don't remember what the title of chapter 3 is, but the section we're going to do, I know that it's 3.1 is what we're starting right now, and this is called derivative formulas and properties. Okay, we shall start with the properties. And by, of course, as is usual, when we say properties, we mean algebraic properties. How do you manipulate them and use arithmetic when it comes to derivatives? What are some rules that we have? So first, let f of x and g of x be differentiable functions. meaning you can find their derivative. Derivative limit exists, just assume there are no issues with it. So they're differentiable on their domain. Let C be a constant. Okay. The following properties hold. So one is called the constant factor property. This is basically the property that says we can factor constants out of derivative. We can factor constant factors. So basically this says the derivative of a constant times a function is the constant times the derivative of the function. You can actually factor out constants, and it's not a problem. So example, we saw that, what are some things that I did tell you about? The derivative of the square root of x is 1 over 2 square root of x. So, for example, if I were to ask you, what is the derivative of 6 square root of x? Well, that is the same as 6 times the derivative of square root of x, which is going to be 6 times 1 over 2 rad x, which, of course, you can cancel in here. And so you would get 3 over rad x, and that would be the answer. Can factor constants out. And in fact, it is, this is something that with a little bit of enough practice, you'll actually get very used to, that you don't have to actually write out all these lines that I just mentioned. It's going to be very easy eventually, if you're studying enough, that you would be able to jump from this line directly to that line. Because you're going to know that 6 is just going to be hanging out there, and I'm going to have that over 2. It'll become 3, and you can just see that in your head. Like if you don't show that when you're showing your work, I'm not actually going to care that much. So that's called the constant factor property. We can factor constants out of derivatives. So if I know how to differentiate a function, I automatically know how to differentiate a constant times that function. Okay, that's a nice property to know. So the second property. This is the sum difference rule. Basically, this is a property that says derivatives can distribute across sums. So if I have the derivative of f of x plus or minus g of x, that is the same as me just differentiating the f first, plus or minus differentiating the g separately. The derivative symbol can distribute across sums. So we do have a distributive law when it comes to the derivative. Let's say, example, we saw that the derivative of 1 over x is minus 1 over x squared. We also saw that the derivative of, who didn't I use yet, x squared is 2x. So this means if someone asks you, what is the derivative of x squared minus plus 1 over x? All right, let's do minus. Then what you can do is you can just take the derivative of the x squared minus the derivative of the 1 over x. You know what that first one is, and you know what that second one is. So you get 2x plus 1 over x squared. Okay, and again, something like this with enough practice, should be pretty easy for you to do in your head eventually. You don't have to like waste time writing it out. Oh, I'm distributing the derivative. I'm doing this. Now I'm doing that. No, it's okay to jump here. So trust me, eventually we're going to be taking derivatives of very complicated things where it's like you don't want to have to sweat the small stuff. You're going to have your hands full with something else. So yeah, you could jump there. But the idea is you have a sum. Just think about differentiating each piece one at a time. You just write it out as you're looking at it. Oh, differentiate x squared, 2x, differentiate that, minus 1 over x squared, and you just write it down in one line. When you get to learn the rules and you know the rules, you'll be able to just kind of do it in your head and it'll flow. So one thing I want you to note, the properties above can be mixed. So you might have a situation where you distribute across sums and you're factoring out constants, and that is totally okay. So example, the derivative of, what if I ask you, what is the derivative of 7x squared plus 5 rad x minus 3 over x? Well, you could realize, oh, in my mind's eye, I know I'm just going to differentiate this, differentiate this, differentiate this. And then I know, oh, that 7, that 5, and that 3, I can actually move them out in front of the derivative. So if I know the rule to differentiate x squared, I can do that. The 5 I can move out. So if I know how to differentiate radical x, I can do that. The 3 I can move out. So if I know how to differentiate 1 over x, I can do that. Then I'm going to, okay, it's 7 times 2x plus 5 times 1 over 2 rad x minus 3 times minus 1 over x squared. And you would get this as 14x plus 5 over 2 rad x plus 3 over x squared. And that would be your answer. And I would say something like this, it's okay to either jump to this line or that line. You probably don't want to have to spend time writing out the line that you're distributing the derivative and factoring out the constants. You just kind of know that that's what happened. You leave the constant alone, differentiate the function beside it, and then you multiply them, right? So you don't have to kind of do anything. Okay, to jump to here or here. Some people might be comfortable going all the way to the last line, and to me, that's fine. Some of you might actually want to take an extra step, write out an extra line to make sure that, give yourself a sanity check. And so you can actually read that as, oh, it's 7 times derivative of x squared plus 5 times derivative of radical x minus 3 times the derivative of that. And because you know all those rules, it makes sense as a check. But yeah, you can mix and match them. Here is something I do want you to note also, warning. Note, we did not say that derivatives will distribute across multiplications, divisions. And that's because they don't. Okay, so again, life lesson. Remember I told you guys very much on day one, sometimes knowing what you're not allowed to do is just as important as knowing what you are allowed to do. So you should know, yes, derivatives distribute across sums. Do not assume that if this were a multiplication, that a very similar thing will happen. Because if that were the case, I would have told you, but I didn't tell you. The fact that I didn't say it and it would be so nice and aesthetic and elegant, chances are it means that it's not true. So students get into a lot of trouble with that. So they'll see like the distributive law, oh, if there's a constant in front of these parentheses, I can just take that constant and put it beside each other. And then they're like, well, something similar probably happens when it's a power, right? In the top right corner, I can just distribute it. Like, no, it doesn't work. That's not true. Just because it works, something similar worked in one situation, doesn't mean that something similar has to happen in a similar situation. It's not the same situation, right? So don't make up rules. I will tell you all the rules you need to know. If I do not write it down as a rule, it's not a rule. Chances are you're wrong and you'll make a mistake. Okay, so I specifically said we can factor out constants and we can distribute across sums. I did not say we can factor out multiplication, distribute across multiplication or division, because that's actually not true. But we're actually going to talk about finding the derivative of products and divisions, don't get me wrong, but just know it's not as easy as just distributing the derivative sign. So that's just something I want to put out there. Let's talk about another useful rule without proof. I'll do a few small proofs, but I'm not going to do a lot of proofs when I come up with these rules. If anyone's interested, I don't know if you would be, and it's okay if you're not, and you won't need to know anyway. When I teach the 1206 version of this class, I actually prove everything. And so if you want to see why these rules are true, you can watch my lectures there. But for now, I'm just going to, there are a lot of things I'm just going to tell you, and you're going to take my word for it on faith. Okay, so another useful rule. The derivative of a to the x is a to the x ln a, where a greater than 0 is a constant. Okay, so example, if I ask you, what is the derivative of 2 to the x? Well, that's 2 to the x ln 2. What is the derivative of 7 to the x? Well, that's 7 to the x ln 7. What is the derivative of pi to the x? Well, it's pi to the x ln pi. What else would it be? What is the derivative of 7 times 3 to the x? Well, I know a derivative rule that I can just leave the constant and multiply by the derivative of the function. That's 7 times 3 to the x ln 3, right? So you can know that. So that's just a rule. Not proving it to you, but that's the rule. You can take my word for it. Anything that looks like a constant raised to an x, that's how you differentiate it. And the constant, of course, the base has to be positive, which we're always assuming anyway, because negative bases and complex numbers we don't want to have to worry about. So whenever I give you an exponential, you can assume that the base is going to be positive. And if the base applies to a logarithm, you can assume that it's positive, but it's also not 1, because like log to the base 1, just it means like you didn't even need a log. It's just everything to the power 1. It doesn't, you just get everyone equals 1. It doesn't make sense. Okay, so now, in particular, to throw back to one of our favorite functions, in fact, the most favorite function in mathematics. I don't know if it's a favorite, but it's the most important. The natural exponential, the derivative of e to the x. Notice that e to the x is a constant that's greater than 0. So this rule applies. So according to this rule, the derivative of e to the x would be e to the x ln e. What is ln of e? What is ln of e?
1.
It's 1, right? Which means if my a equals e, then the log part just becomes 1, and you kind of don't see it because you don't have to write multiplication by 1. So you end up with the derivative of e to the x is e to the x. And this is one of the reasons why this function is very special in mathematics. This function, or a constant times this function for obvious reasons, is the only non-constant function that is its own derivative. The only other function that shares a similar property is the zero function, y equals 0, which a lot of times just isn't very interesting. But here we have an exponential function, and exponentials are very useful for all sorts of things. And here we have a very special exponential function that is its own derivative, which is, it's crazy. So here's a function where its position tells you what its current speed is. Oh, it's now at position 5. How fast is it moving? 5 units per second, right? Like, so it's a very interesting aesthetic property. And yeah, derivative of e to the x is e to the x. That's something that we know now. Derivative of a to the x is a to the x ln a. So in particular, when a is a positive constant, not being e, but including being e, that would apply. You would get this in the case that it's e because the log part becomes 1. Okay, another thing that I'm going to tell you, which you are going to take on faith, is one of the derivative rules, which was mentioned earlier, the chain rule. Super important derivative rule. Now, this rule tells us, this is a rule for differentiating composite functions. Now, remember what composite functions are. These are just functions inside of functions, like f of g of x, right? So the rule is, if I wanted to differentiate something that looks like this, I have one function and there's another function plugged inside of it. How do I differentiate such a thing? The chain rule would tell you, and again, I'm not going to prove it, just going to tell you, the chain rule says, here's how you would do that. You would differentiate the outer function, leaving the inside intact. Then you would multiply by the derivative of the inside function. So here you take the derivative of the outer function, leave the inside, like students just often are very tempted to start differentiating the g right away. You're not supposed to do that. Leave the inside alone at first. Then you multiply by the derivative of the inside. This rule, very super duper important, is called the chain rule. Yes, and it is something that we know now. Just memorize. That's why I'm gonna put a box around it. You should know that's the chain rule. That's how it's done. Let's see, maybe an example. Let's suppose our f of x equals the square root of x, and g of x equals 1 minus x squared. Then, of course, your f of g of x, which we know how to compute since pre-calc, is just the square root of 1 minus x squared, because that's how composite functions work. So now the question would be, all right, if someone had given that to me, what is the derivative of the f of g of x? That is the derivative of this function. Now, whenever you see something like that, you should be able to identify it as a composite function, because it's not just radical x, right? It's radical of a whole other thing, right? So it's like you took a whole thing and you plugged it into radical x. So here you have this guy here is your inside function. And this guy here is your outside function. Right? And so that's how you kind of look at it. So if I were to tell you or ask you, find the derivative of the square root of 1 minus x squared, well, what do? We differentiate the outer function. How do we differentiate the outer function? How do you differentiate square root of x? It becomes 1 over 2 radical x, right? So here we go 1 over 2 radical blah, right? Do not touch the inside. So you do not touch the inside, you differentiate the square root around it. Then you worry about the inside. You multiply by the inside. Of course, you want parentheses here. So here you're going to have this guy. You want a derivative of the inside. Is what you're going to put in here. Now, how do we differentiate 1 minus x squared? Well, that's a sum. Derivatives distribute across sums. So I can just differentiate one at a time. What is the derivative of 1? It's 0. Why? Derivative of a constant is 0. Jhevon told us that like 3 classes ago. Minus, what is the derivative of x squared? 2x. So we have that. So ultimately, we now have 1 over 2 radical 1 minus x squared times minus 2x. Of course, the x's can, the 2's can cancel. And so now the final answer is going to be minus x over the radical of 1 minus x squared. And that's the derivative. That is the slope of that function. So if your function is 1 minus x squared, minus x over the radical of 1 minus x squared is going to tell you the slope of the tangent line at any point to that curve, whenever that exists. Obviously, it's not going to exist when our x is 1 or minus 1. It's also not going to exist if our x is outside of minus 1 or 1. It'll only work for x's in between, strictly speaking, in between minus 1 and 1 is where this derivative is going to exist. But this function only exists for x between minus 1 and 1 inclusive also. So yeah, the derivative just doesn't work at the endpoints because to find the derivative, you need to take a limit, but you don't have a left and a right. So that's why the derivative itself doesn't work at the endpoints, even though the function does, because this is actually like a, this is actually like a semicircle, right? Right, of radius 1. So it works there, but obviously at the endpoints, you can't take a limit because at minus 1, there's no left limit, and at 1, there's no right limit. So the limit is not going to exist as you approach -1 or 1. And so the limit of the derivative isn't going to exist either. And that's why the derivative itself is not going to work at -1 or 1. You'll notice that if you plug in -1 or 1, you would get division by 0. So yeah, just an interesting thing to point out. Let's do another example with the chain rule. What if I asked you to differentiate radical x plus 1 over x squared? Okay, now, turns out there are 2 ways to do this. One, you can expand and differentiate each term. Right? We know how to expand a square, right? So you can have the derivative of radical x plus 1 over x squared. We know how to square that very quickly. You square the first term, multiply 2 by that term, then you square the second term, right? And I mean, this can, do we actually know that? You guys don't know how to do that yet. I didn't tell you guys how to do that. Let me write this out. I mean, I'll tell you the answers. In the future, when I give you some more rules, you'll realize you would deal with this by rewriting them as powers. And then it's going to be something like this. We haven't learned this yet. But you will. By Friday, for sure, you'd be very comfortable with doing that kind of maneuver. The other way is to use the chain rule. Because now, even here, you'll realize that without the chain rule, we don't even have enough knowledge to answer this question yet. But it turns out with the chain rule, we actually do. And it's actually going to be easier on top of it. So if I say the derivative of radical x plus 1 over x, notice that the square is the outer function. And this guy is the inner function. Right? So I know how to differentiate a square. It's 2 times the thing, right? Derivative of x squared is 2x, right? But I leave the inside alone. Then I multiply by the derivative of the inside, which is a sum of 2 things. I just differentiate one at a time. I know the derivative of radical x is 1 over 2 rad x. And I know that the derivative of 1, I know the derivative of 1 over x is minus, come on, pencil, minus 1 over x squared. And that would be the answer. And if you were to actually multiply this out, you'll actually get the same thing. I could do it, but I don't want to bother. So yeah, that would be the chain rule. Here's an example. Differentiate the square root of x plus 1 over x, which is very similar, but it's raised to the 100. Now method 1 doesn't look so good anyway, right? Could make a drinking joke here, but we're not going to. Yeah, chain rule. Like this, if I were to do method 1 and use algebra and stuff and multiply everything out, I'll be multiplying out all day. I'll get 101 terms and then have to differentiate 101 things. I mean, if I'm a computer, it's not really a problem, but I'm just some kid trying to pass this class. You know, Jhevon's giving me a hard time. I'm trying to get through this. I'm trying to survive, you know, and I'm just trying to get through this test in the required time. So I don't want to do this. But with the chain rule, it's still not that big a deal. It's actually not much different from the other thing, although technically, again, I didn't tell you what this would do. But the chain rule would tell you that this guy is going to be that. The derivative of something to the 100th power is 100 x to the 99th power. We haven't learned this yet, but we will. So that's how I got that. Yeah, and that's just a chain rule. here is another important thing. The chain rule is also useful in getting us to generalize our rules. So what do I mean by generalize? Let's take a rule that we already know. So we know, so this is a very easy rule. The derivative of e to the x is e to the x. But what about something like this? Derivative of e, not to the x, but some other function, g of x. Well, thinking of g of x as an inside function, I took a function g and I plugged it into the e to the x function. Well, the chain rule says you differentiate the outer function. When you differentiate e to the x, what happens? Nothing, stays e to the x. So you differentiate the outer function, and it will just stay as itself. You leave the inside alone. Then you're going to multiply by the derivative of the inside, right? Or in other words, that's going to be like g prime of x times e to the x, e to the g of x. In other words, the derivative of e to a power is the derivative of the power times the original exponential. So this leads to a rule now that we can say, yes, it's cool that you know the derivative of e to the x is e to the x, but what's cooler is for you to know that the derivative of e to the u is u prime e to the u. See, that is far more general. U is any function. Differentiable, of course. Okay, so once you know how to differentiate the function that's in the power of the e, you'll automatically know how to differentiate e to that power, right? So if I have the derivative of e to the x squared, what is that? I know how to differentiate x squared. It's the derivative of the power times the original function. Done. What is the derivative of e to the radical x minus 1 over x? Well, that's just going to be the derivative of the power times the original function. That's how you differentiate exponentials, right? Which is very nice, very nice. We can also generalize the other function. Also, we can generalize the derivative of a to the u. Let's pretend it's not just a to the x, it's a to the u and use some random function. X is still my independent variable, but my u could be some other function. Then that is going to be u prime, the derivative of the inside, times the derivative of the outer. So example there. We saw how to differentiate 2 to the x. That was just 2 to the x ln 2. However, if I had, say, 2 to the x squared, then the derivative of that would be 2x times 2 to the x squared times ln 2. So this would be like the u prime. This is the 2 to the u. This is the ln of 2. And that's the chain rule. You just follow the overall rule, leaving the inside alone, and then you multiply by the derivative of the inside. And you can generalize a lot of rules like that as well. If brain space is a concern, it is better to memorize the chain rule versions of rules. They include the basic versions. So let's say if I memorized, example, let's say I memorized the derivative of e to the u is u prime e to the u, and then someone came back and asked me the basic rule, what is the derivative of just e to the x? Well, that's just going to be 1 times e to the x, where that 1 comes from the derivative of x. Right? And this is the e to the u original function. So I can know that the derivative of e to the x is e to the x. Like if I know the chain rule, it's a more generalized rule. And pretty much you take the chain rule and you can turn it into a basic rule by turning the derivative part into a 1 and the u part into an x. Right? So if you had to memorize one of them, I would memorize the chain rule versions of these rules. They go better. Let me set up some other rules for you. What is, set up a couple in the last few minutes and then we'll go. Another important function was the natural log. How do we differentiate the natural log? Well, I'm not sure, but I know how to differentiate its inverse, the exponential. So let's actually use that. Set y equals ln x. We want y prime, which is the derivative. This, of course, would mean that e to the y equals x. So this is just me rewriting with the log rule. Then what I can do is I can differentiate both sides. Derivative of e to the y is y prime times e to the y by the chain rule that I just mentioned. Derivative of x is 1. And so now what that means is my y prime is 1 over e to the y. E to the y is never 0, so dividing is cool. But what is e to the y? E to the y is x. So this means my y prime equals 1 over x. That's the derivative. So the rule is the derivative of ln x is 1 over x. Now, of course, x cannot be 0. But the x couldn't be 0 in the first place because it was already inside a log. So it's not bothering us. And of course, x here had to be positive if it's if the log doesn't, if the x doesn't have like an absolute value around it or anything like that. So that's the rule. And chain rule version, this is not my final form. The derivative of ln of something is the derivative of the thing over the thing itself. So you just take the 1 over u, multiply by u prime. You get u prime over u. So example, what if I wanted to differentiate the logarithm of, say, x squared plus 1 over x plus 2? Well, I put that thing in the bottom. And then on the top, I write the derivative, 2x minus 1 over x squared plus 0. And that's that. I mean, you could simplify, but that's the answer. So yeah, that's that. So that's how you differentiate a logarithm. I mean, could also just brush through that, but we'll stop there. So those are some derivative rules and how we're going to compute them. And you realize now that just knowing a few basic rules, there are all sorts of crazy things we can already differentiate and find the slope of. And we're going to give, I'm going to give you more rules next time where you're going to be able to even attack way crazier functions in these. So next time we'll talk about the infamous power rule, as well as the rules that will allow us to deal with products and divisions, because we actually don't have any yet. But that being said, this is where we will end. This is where the journey ends. Hopefully that was fine. And remember, no class tomorrow, so I'll see you guys on Friday. All right, so have a good day. See you guys in the next one. Ciao.